All right, today in Concept E, we're going to be focusing on some different concepts related to bonding, something called hybridization, and another idea about sigma and pi bonds. So this is a theory, so science believe that this is a good possibility of what happens in an atom. And this relates to covalent bonds. So covalent bonds form when the orbitals of two atoms are going to overlap and a pair of electrons occupy the overlapped region between the two atoms. The space formed by the overlapping orbitals can accommodate a maximum of two electrons, and these electrons must have opposite spins. This goes back to kind of an idea of our atomic theory unit when we discuss how our electrons are arranged in orbitals. Basically, the greater the orbital overlap, the stronger the bond. So we can have different combinations, and these are just some of them. We could have two s orbitals that overlap, such as when we make diatomic hydrogen. We can have an s and p overlap, or we can have two p overlaps. Either depending on the direction of the p orbitals, they can overlap between the axi or above and below the axis between the two nuclei. So these different overlaps, we do give different names, and the first one is a sigma bond. So a sigma bond is formed by an end-to-end overlap of the orbitals. So think about like the overlap of the s and s or s and p, where we have this direct end-to-end overlap. The electron density of a sigma bond is greatest along the axis of the bond, so directly between the two nuclei. We count all single bonds as sigma bonds. So in this example in your packet, I have 7 single bonds, so that means I have 7 sigma bonds present in that compound. Pi bonds are a little bit different because they form by sideways overlap of the orbitals. So here in the green orbitals, that's a sigma bond that's directly between the nuclei. A pi bond is going to form above and below the nuclei from this sideways overlap of each of their p orbitals, and 2 electrons will move through both of that. So this is representing a single pi bond above and below. A pi bond does tend to be weaker than a sigma bond because the sideways overlap is less effective than the end-to-end. You don't get as good of an overlap. In a double bond, the first bond formed is a sigma bond, and the second bond formed is a pi bond. So in counting these, it's a little bit trickier. I first identify any double bonds. I have one in the center here between the carbons. The first bond is going to be a sigma bond. So that first line, doesn't matter, top or bottom, I'm going to count as a sigma bond. So that's my 1, and then I have 2, 3, 4, 5. That's my 5 sigma bonds. The second line in the double bond is going to count as my pi bond. So I only have 1 pi bond in this structure. A triple bond contains 1 sigma bond, the first one formed, and then 2 pi bonds. So in this triple bond that I have, the first line is going to count as a sigma bond. So that's 1, 2, 3, my 3 sigma bonds. The other 2 lines in the triple bond are going to count as 2 pi bonds. So in this example here, I have 2 pi bonds and 3 total sigma bonds. All right, so you should be able to count sigma and pi bonds if given the structure, or if you're asked to draw it, being able to relate it to that. Hybridization is a theory. This is how scientists account for the different shapes that we're going to see later next week when we go to do a later concept and discussing molecular shapes. So the orbitals that form when bonding occurs are different than the atomic orbitals that we know about in isolated atoms. So in isolated atoms, we talk about the s orbital, the 3p orbitals, the 5d orbitals. But when they actually go to bond, scientists believe that something happens to those orbitals. They believe atomic orbitals mix, or what we call hybridize, when bonding occurs to form hybrid orbitals. And hybrid orbitals means that they're all equivalent to each other. The shape and orientation of the hybrid orbitals not only maximizes overlap, but it also determines the shape and angles between all the bonds in that molecule. Now, carbon as we know it has 2 electrons in 2s, and then 2 electrons in 2 different 2p orbitals, and we can see the Lewis dot structure here. However, we know that this wouldn't allow for carbon to make 4 bonds that we know carbon usually makes. So what scientists believe happened is that the 2s and the 3 2p orbitals mix together, and these are set up in terms of energy. So they believe they mix together to make 4 equivalent orbitals, where it then has 1 electron into each and allows for it to share an electron and make those 4 bonds. Those 4 equivalent bonds then, which are a mix of 1s and the 3p orbitals, we refer to as sp3. So when we come up with these hybridizations, it really is just as simple as counting how many bonds you have, or how many what we're going to call electron domains, and being able to just count through your s, your 3p's, and some of the d orbitals. So you're going to hear a lot of talk about electron domains. Electron domains are basically going to relate to how many orbitals become hybridized in setting up our various molecules. An electron domain can include a bond or set of bonds. So a single bond counts as one domain, a double bond counts as one domain, and a triple bond counts as one domain. Also, a lone pair of electrons will count as a pair as a single domain. So let's look at some examples. When we do these, we're always focused on the central atom. So beryllium is in the center here. We're going to count how many domains it has around it. Beryllium only has two bonds connected to it, so 2 domains. So now I'm going to count up, starting at our s orbital. For my 2 domains, that means I'm going to include s and the first p orbital. So that means I have an sp hybridization. So 2 orbitals, I should have 2 orbitals here. In this boron example, I have 3 bonds around it, which means I have 3 domains. So I'm going to count up starting at s. So I have s and 2 p orbitals. So that means then my hybridization is going to be sp2. So this number of orbitals here, s, and my 2 p's, should account for the 3 domains around boron. Here we have 2 examples where we have 4 domains. In the first one with methane, we have 4 bonds. Okay, that means then that I'm going to mix 4 orbitals, s and 3p, which means my hybridization is sp3. In this example with water, I have 2 bonds, and I also have 2 pairs of electrons. So I have 1 domain, 2 domains, 3, 4. So this is another example where I have 4 electron domains. So same thing, I'm going to be mixing s and 3p orbitals, which means I have a hybridization of oxygen being sp3. In these final 2 examples, you're going to see just additional bonds here, and we'll talk about that in just a second. Phosphorus has 5 bonds around it. That means 5 orbitals had to hybridize. When those orbitals are mixed, that means that I'm going to start counting at s. So I have s, my 3 p's. I don't have any more than the 3 p's, so I then jump up and include 1 d orbital. So my hybridization is sp3d. In this next one, sulfur hexafluoride, I have 6 bonds, 6 electron domains then, which means that I'm going to include a second d orbital. So my hybridization is sp3d2. So let's take a look at some of the examples that you saw a little bit closer and just talk about why the structures are the way that they are. Because as you can see from that chart, you should have noticed that there are some molecules that do not obey the octet rule. The first set are what we consider incomplete octets, where they're electron deficient. They can actually hold less than expected. This includes 2 examples that we tend to not even really think about necessarily as covalent bonding, because we tend to think about them as a metal or a metalloid. But because of their size and differences in their electronegativities and ionization energies, they do actually form covalent bonds. Beryllium has 2 valence electrons, boron has 3 valence electrons, and can often accommodate only 4 or 6 electrons respectively. So beryllium needs to make these 2 bonds to have 4 electrons around it, and boron needs to make just these 3 bonds to get 6 electrons around it. Again, this is an exception to octet rule. Okay, these are 2 that you should definitely be aware of and memorize as ones being electron deficient. We can also very commonly make expanded octets. These are elements with an expanded valence shell where they can hold and accommodate more than 8 electrons, often 10 or 12, in their Lewis structure. Now the thing you do need to memorize, this can only happen in elements that are in their 3rd period and below, meaning the 3rd, 4th, 5th, so on, because they have the availability of the empty d orbitals in their valence shell. So it allows them to hybridize with those d orbitals and accommodate and make more orbitals to bond. This usually incorporates a very large central atom, and it's usually going to be bonded to really small electronegative atoms like fluorine or chlorine, because it again allows that number of atoms to go around the central atom. So we saw an example where we had phosphorus in the center. It was able to create those 5 bonds with the small electronegative chlorines, and then sulfur was able to make 6 bonds with the small electronegative fluorines. So we'll be working on those tomorrow as well, being able to draw these expanded octets, so you can kind of start to get the hang of how these will all connect, because there's a lot of examples of them. All right, you're all set.